Sauce here. This is a video lesson on a family of functions we call logarithmic. We're going to start with something that's familiar. I have an exponential function written here. Y is equal to 10 to the x. We call this exponential because the variable is in the exponent position of a power whose base is 10. This is the parent exponential function. And though some might feel that a power of base 2 would be a little simpler, because we have a base 10 numbering system, we're choosing base 10 to be our most basic form. So where does a logarithm come from? We know how to take inverses. We need inverses because inverse operations help us solve equations. The inverse of an exponential is logarithmic. Logarithmic is defined to be the inverse of exponential. So how can we get to the inverse from this equation? We do the familiar switch of the variables and then solve for the new y. How would I get y by itself? I have to undo this power base. What is the inverse of a power base? A log base. And I can show my work by taking the log base 10 of both sides. I use the abbreviation log, and I put the log base as a little number to the right and lower. We call this subscripting. And then what I'm taking log base 10 of is the side x. What I do to one side, I have to do to the other, so I'm going to take the log base 10 of what's on the right side, and that's the power 10 to the y. I've done this so that I can get y by itself. Power base 10 and a log base 10 are inverses of each other. They cancel out. Just like adding one and subtracting one cancel out. Just like dividing by 2 and multiplying by 2 cancel out. Log base 10 cancels a power base 10, leaving y by itself. Now on the other side, we can't evaluate this. We have a variable x. But what we've come across is the simplest form of logarithmic equation. This is parent log. It is a logarithmic equation whose base is 10. We can also come across an inverse graphically and visually by a reflection. So if I start with my exponential function and graph it, it's going to be a curve that grows very slowly when x is negative, intersects the y-axis at 1, and then grows very, very quickly afterwards. I've graphed the exponential equation y is equal to 10 to the x. And I can find an inverse of a graph as a reflection over the line y equals x. When I do that, I will get the same shape of curve, but it is growing gradually and then turns a sharp corner going through the x-axis at x equals 1, and then seems to level off as it approaches 1. This will continue to grow very slowly. This is the inverse of the exponential function. It is y is equal to log base 10 of x. Log base 10 is a little bit special because it's the most common log base to use. So we have what we call common log, and that is log base 10. And because common log of base 10 is the most useful in most algebra processes, when we write a log without bothering to show the little number of the log base, then it's implied that it is a log base 10, a common log. So if you don't see it, if you see a log written without the number, it's because it's 10, so you know it to be 10. It's like using the radical symbol. If we wanted to write a cube root, we need to put a little 3 in the V of the radical symbol. But if you don't see a number written in the crux of the radical symbol, it's a square root. It's implied that that little number ought to be a 2 if you don't see it. If you don't see it in a log, it's base 10. We can have other log bases. We could say, generically, log base b, where b can be anything of x. And symbolically, we mean log with the base that we're talking about. In this case, b can symbolize any number, log base, of x. Looks like this. And if we make it an equation, then we have a general logarithmic equation of any base. The inverse equation of log base b of x is equal to y is the power base b to the x. And this ought to look like the familiar power whose base is b to the x is equal to y. These are inverse equations. There's a general family of logarithms and general family of powers, or exponentials. And notice that in each we have this idea of its base, b. If I change the base, then the curve will be similar. But if we have a lower base than 10, like 2, then the curve is going to be more gradual. I can roughly sketch the curve of 2 to the x by showing that the curve is wider. It's more gradual in both directions. The curve that I just drew here is a sketch of the exponential y is equal to 2x. Same kind of exponential curve, but more gradual, broader, lower power base. Similarly, if we have the inverse of 2 to the x, it's log base 2 of x, then it's going to be the same logarithmic curve, but again, more gradual. Lower log base, more gradual curvature. Higher log base, sharper curvature, but essentially the same shape of curve. This here is a sketch of y is equal to log base 2 of x. Let's get a little more practice solving equations with exponentials and logarithms. We could have log base 2 of x is equal to 3. There's one variable here. I ought to be able to use algebra to solve for it, which means get it alone by itself. What's being done to x is an operation, log base 2. Be careful, this 2 and this x are not a power. We would not read this log of 2 to the x. That's misunderstanding the notation. So this is not the log of 2 to the x because we don't read this as a power 2 to the x. This is a log base 2, and that log base 2 is doing, it's doing it to x. Now how do I get x by itself? A log base is the inverse of a power base. So to undo a log base 2, I need to power base 2 both sides. That looks like this. Writing a 2 so that what I have on the side is now a power whose base is 2. This power base 2 and log base 2 will cancel out because they're inverses, leaving x by itself. And on the other side, I've created a power whose base is 2, and I think of this as 2 to the third. 2 times 2 times 2 is 8. One more. 10 to the x is equal to 100. Now, hopefully, we already know intuitively, because we can do it in our heads and find x. What power of 10 is equal to 100? I raise 10 to what power to get 100? 2. X is going to be equal to 2. But let's show our work in getting there. If I wanted to solve for x, I need to undo this power base of 10. The inverse of power base 10 is log base 10. And remember that log base 10 is what we call common log. So if I'm going to show my work, I'm going to take the log of this 10 to the x. And notice that this time I didn't write the little number that represents the log base. It's because it's base 10. If we don't see it, it's base 10. On the other side, I'm taking the log, or the common log of 100. Log base 10 and power base 10 cancel out, leaving x by itself. And the log base 10 of 100 is 2. How do we know? Well, we could key this into a calculator. In order to evaluate most logs, we'll need a calculator. But remember, we know that x was going to be 2 because we know that we need to square 10 to get 100. When working logarithms, it's very often helpful to convert an exponential form to a log form or vice versa. In this case, we had a logarithmic equation and we turned it into an exponential. Here we started with an exponential and we turned it into a log in order to evaluate.